Hello again, Gen Chemers. Here we are again with a second lecture on Module 2. So let's get started. I'm going to share my screen. And I'm going to get rid of my thumbnail. All right. So the first lecture was all about the history of how atomic theory developed and how we know that the atom has a nucleus and has various subatomic particles, which are electrons, protons, and neutrons. So we're going to go and use that information now and look more at atomic theory and how the atom is important in chemistry. So all atoms are composed of the same subatomic particles. We have the protons, we have the neutrons. These are found in the nucleus. This is outside the nucleus. Protons and neutrons have all the mass, whereas the electron cloud is due to the volume, or is predominantly responsible for the volume of the atom. So let's look at these masses. Protons, one individual proton is 1.67262 times 10 to the minus 27th kilogram. One individual neutron is about the same size. It has slightly more mass. But look at our electron. Our electron is orders of magnitude lower in terms of the mass. Compared to the mass of the proton and the neutron, the mass of the electron is actually negligible, which is why we can say that the mass of the nucleus is actually responsible for the mass of the entire atom. The charge on the proton and the electron is equal in magnitude, but opposite in sign. The neutron, remember, has no charge, right? The neutron is neutral. So this is another mass unit that we use. It's called atomic mass units. This is what we're going to sort of focus on when we look at masses on the periodic table. This is the kilogram mass for the different particles. This is the part that we're sort of gonna be focused on more so than any of these kilogram masses. Notice the proton is +1, the neutron is neutral, and then the electron is -1. And again, the charge on the proton, the charge on the electron is equal in magnitude, opposite in sign. When we consider elements, like the elements off of the periodic table, the most important number is the number of protons in the nucleus. The number of protons defines the element. Carbon has 6 protons. If I don't have 6 protons, I don't have carbon. The number of protons defines the identity of the element. Now, the number of protons is called the atomic number. It's listed on the periodic table, and the symbol for the atomic number is a Z. Here's what I mean when I say the number of protons defines the element. Here I have the element helium. That's atomic number 2. It has 2 protons in the nucleus. Helium is, on the atomic level, has 2 protons in the nucleus and 2 electrons because it's electrically neutral. Carbon, which is a different element, atomic number 6. It has 6 protons in the nucleus. Those are the red balls there. The blue balls are the neutron in that nucleus. This carbon atom has 6 protons. If I don't have 6 protons, I'm not carbon. Helium has 2 protons. If I don't have 2 protons, I'm not helium. So the number of protons actually defines, identifies the element. Now, you're probably all familiar with a periodic table, given that you needed to have some chemistry as a prerequisite to take this course. Regardless of what periodic table you look at, you're always going to see an atomic number, the chemical symbol, and then the name. If I'm really devious, I could give you a periodic table that doesn't have the name and just the chemical symbol. There are chemistry classes that do that. I don't quite see the point to that because you can always have a periodic table at your disposal. So the periodic table that you're going to use is going to look something like this. Since it's an online class, periodic tables that you can find on the internet will have varying information and maybe be formatted a little bit differently. But I always have the atomic symbol, the chemical symbol, or the atomic number, the chemical symbol, and usually the name also. Every element is identified with a unique atomic number. Remember, the atomic number is the number of protons. As I add or increase the number of protons, I change the identity of the element. So each element has its unique chemical symbol. This is either going to be a 1 or a 2-letter abbreviation. For example, helium is HE, and the first letter is always capitalized. The second letter, if there is one, is always lowercase. Carbon is C, nitrogen is N. You do have to look at the periodic table once in a while. Look at the periodic table periodically in order to get familiar with where the location of various elements are. Okay, let's look at something called an isotope. Remember, my atomic number is the number of protons. Now, because atoms are neutral, unless they lose electrons to form ions, but generally, atoms are going to be neutral. So, the number of protons has to equal the number of electrons in order to get a 0 charge. So if I know the atomic number, in the neutral atom, I also know the number of electrons that are zooming around the atom's nucleus. There's another characteristic called the mass number. This is given a designation, the letter A. Now this is important. This is the sum of the protons and the neutrons in the atom's nucleus. Remember, the mass of the atom resides in the nucleus, and the mass is due to the protons and the neutrons, which have about the same magnitude of mass. So the mass number for an atom is going to be the sum of the number of neutrons and the number of protons in that nucleus. An isotope of an element is the same element, right? So I have identical atomic numbers. So I have the same number of protons because that is the identity of the elements. But I have different mass numbers, which means I vary in the number of neutrons. in that nucleus. Now, the relative amount of each different isotope in a naturally occurring sample of a given element is roughly constant. So generally, all samples of carbon, regardless of where they're found in the world, is going to have roughly the same distribution of the types of isotopes of carbon. These percentages are called the natural abundance of these isotopes. Now, what's interesting is you can actually figure out the mass of a given atom by using something called mass spectrometry. And this technique has become so precise that it has allowed such accurate measurement that reveal there are actually small but significant variations in the natural abundance of isotopes for many elements, which means it really depends on where the source of the atom is from. Right, so depending on the source, you're going to have small but significant variations in the natural abundance of those isotopes. We're really not going to worry about that in this class. When I give you isotope problems, I will give you the natural abundance that you're supposed to use in those problems. But just recognize that advances in mass spectrometry have allowed us to actually see very small variations in these natural abundance percentages of isotopes depending on where they're sourced in the world. Let's go over this a little bit more thoroughly. We know hydrogen is atomic number 1. So it has 1 proton, and in the neutral hydrogen atom, it has 1 electron. There's actually 3 different isotopes of hydrogen. I have protium, which has 1 proton and no neutrons. So 1 plus 0 equals 1, which is the mass number. I have deuterium, which has 1 proton and 1 neutron. 1 plus 1 equals 2, which gives me that mass number. So here now I have a proton and I have a neutron in my nucleus. And then I have tritium, which has 1 proton, and I actually have 2 neutrons in the nucleus. 1 plus 2 is equal to 3, which gives me a mass number of 3. So these are 3 different isotopes of the element of hydrogen. They have different mass numbers, but they all have 1 proton because that's the identity of hydrogen. I can use this symbol. This is a nuclear symbol because it tells me what's going on in the nucleus. I have the atomic number, which is the number of protons. I have the mass number up in the left, top left, which is the number of protons plus the number of neutrons. And then I have the chemical symbol. So this would be H11. This would be H12, and this would be H13. And this would be how I designate those 3 isotopes of the element hydrogen. So again, the mass number is the top left. The atomic number is the bottom left. I can tell when I have carbon 12. So this is the symbol, right? 6 protons, 12 protons plus neutrons. I have 6 protons because it's carbon. I have 6 electrons because it's neutral. I have 6 neutrons because my mass number minus my atomic number, which is the number of protons, is equal to the number of neutrons. So here I have 12 minus 6, which gives me 6 neutrons. If I have another isotope of carbon 14, which again has this different mass number, This now 6 protons because I'm carbon, 6 electrons because this is the neutral atom of carbon, 8 neutrons because I have 14 neutron or mass number minus 6 protons, which gives me 8 neutrons. So if I have this nuclear symbol, I can actually figure out the number of protons, the number of electrons in my neutral atom, and also the number of neutrons as long as I have the mass number. A second common notation for isotopes is where I have the chemical symbol followed by a dash followed by the atomic number. So I could have the 3 isotopes of neon being read as Ne20 or neon 20. And again, what I'm going to know is that this is the mass number. So this is the number of protons plus the neutrons. Because it's neon, I know the number of protons off the periodic table. Neon is atomic number 10. Every isotope of neon has got 10 protons. Neon 20 has 10 neutrons. Neon 21 has 21 minus 10 or 11 neutrons. And neon 22 has 22 minus 10, which gives me 12 neutrons. This is the natural abundance. 90.48% of all neon is the neon 20 isotope. Only 0.27% is neon 21, and a little more, about 9.25% is neon 22. So this is the most abundant isotope for neon. So here's some practice. Using the format A-X, write the symbol for the nuclide having 26 protons and 30 neutrons. Well, if I have 26 protons, I'm going to go to my periodic table. I'm going to look at atomic number 26. What I'm going to find out is atomic number 26 is iron, or Fe. So I could write iron. Now I have 30 neutrons. This X is the mass number, which is equal to the number of protons plus the number of neutrons. So that's equal to 26 plus 30, which gives me 56 as my mass number. Oops, that's the atomic number. So what I'm going to write is iron 56, or I could write iron 56, or if I wanted to use the other format, I'm going to write this as a description of this particular isotope. Here I'm asked to use the other format to write the symbol for the nuclide. This is just that particular atom, which has different particles in the nucleus, which is why it's a nuclide. So if I have 15 protons, this is my atomic number. If I have 15 protons, I am phosphorus. So phosphorus is designated with a P. I have 17 neutrons, so my mass number is going to equal to 15 plus 17, which is equal to 32. So I have phosphorus, atomic number here, mass number there. I could also call this phosphorus 32 or phosphorus 32. Those are all indications of the isotope that I'm looking at. Now, if you look at the periodic table, you're looking at masses that are designated on the periodic table. Those are not masses of individual isotopes. The mass that's listed for an element on the periodic table is the weighted average of the atomic mass of all isotopes of the element. I can calculate this if I know the natural abundance and I know its mass in atomic mass units. And we're going to look at how I can calculate those numbers. Remember, the natural abundance is usually in a percentage, and that is the proportion of a particular isotope that is found in nature. So like we said before, about 90% of all neon atoms in nature were neon 20. So here's how I can calculate the average atomic mass. This is the sum of, this is the number of terms that you might have. So if I have 2 isotopes, I have 2 terms. If I have 5 isotopes, I'm going to have 5 terms. This is the fraction, which is the percentage divided by 100. So I have to have a decimal, right? I have to have a fraction of isotope n. And then this is the mass in atomic mass units. And then depending on the number of isotopes that I have, I take the product of the fraction of the isotope times the mass of the isotope, and then I just sum those products in order to get the average atomic mass, which is what is usually seen on the periodic table. Here's an example using neon. Neon 20 has an atomic mass of 19.9924, and it has a natural abundance of 90.4838%. I'm going to make that a decimal. I divide by 100, so I move my period over, my decimal point over by 2 units. So that's how I get this 0.904838. So this I'm going to move over 2 again, so I get 0.00. Basically, I take the percentage and I divide by 100 to get the decimal. Once I get all those products, so this is the product of the abundance times the mass of 20, plus the product of the abundance times the mass for 21, plus the product of the abundance times the mass for 22. When I sum those all up, I get the average weighted atomic mass for neon, which is 20.1799 to the correct number of significant figures using this data. And if I look at the periodic table, what I'm going to see is that neon on my periodic table says 20.8180, which is a little bit fewer significant figures, but you get the idea of how I get those numbers that occur on the periodic table. Now, I can actually do problems like this using that same formula. Let's say I want to calculate the average atomic mass of chlorine. Chlorine is atomic number 17. I have 75.77% of chlorine 35 atoms. These atoms have a mass of 34.97 AMU. I have 24.23%. This is my natural abundance of the chlorine 37 atoms. And this is the mass of that particular isotope. So the average atomic mass is going to be the mass of isotope 35, which is 34.97 AMU, times the fraction of the percent abundance, which is 0.7577, plus the mass of the next isotope, which is 36.97 AMU times the decimal form of the percentage, which is 0.2423. When I do this math, what I'm going to get, go get my calculator. When I do this math, I'm going to have 34.94 times 0.7577 plus parentheses 36.97 times 0.2423. And what I get is, let me do this again, 35.359. Okay, I think I did something wrong. Let's look at this again. I have 34.95 times 0.7577. That gives me 26.481615 plus, if I have 36.97 times 0.2423, that gives me plus 8.95831. I sum that up and I get 35.439446. I want to go to 4 significant figures. So I get 35.44 atomic mass unit as the average atomic mass. If I look at chlorine, I have 35.453. I'm pretty close to that number, and that's how I actually would calculate the average atomic mass. If I have something like magnesium and I want to calculate the average atomic mass, here I have 3 isotopes. I have 3 isotopes, so I have 3 terms. So I'm going to have 23.99 AMU, which is 0.7899% abundance, plus I have 24.99 AMU times 0.1000. Then I have plus 25.98 AMU times 0.1101. And when I sum all of this up, I'm going to go ahead and get the average atomic mass for magnesium, which should be 24.305 when I do all the math. I'm not going to do the math here. I'm sure you can plug that into the calculator to show and convince yourself. I just showed you basically how to set this up. Here's another example, which is a little bit different. Let's say I know I have gallium and I know I have 2 isotopes. I have gallium-69, which has a mass of that. I know the natural abundance for gallium-69. I also know that there's a second isotope, which is gallium-71. So using the atomic mass, find the mass of gallium-71. This is a little bit more complicated. It's a little bit twisted. I know I'm going to set it up the same way that I did before. If I look at gallium on the periodic table, it's atomic number 31. My mass is 69.723. So 69.723 AMU, which is off the periodic table, is equal to the mass of gallium-69 times the abundance of gallium-69 plus the mass of gallium-71 times the abundance of gallium-71. Now, I know this because that's this guy, and I know this because that's this guy. So 69.723 is equal to 68.9256 times 0.6011. But how do I get this? This is what I'm actually solving for. Do I know the abundance here? The key here is I have two isotopes. So the percentage of gallium-69 plus the percentage of gallium-71 has to equal 100. So the percentage of gallium-71 is going to be 100 minus 60.11, which is going to equal 39.89. So now I have this term. So I'm solving for the mass of gallium-71, and I know the abundance is 0.3989. So if I do this, I get 69.723, 68.9256 times 0.6011 is equal to 41.43117816 plus 0.3989x, where this is x. So now I'm going to subtract my periodic, my 69.723 minus my 41 is going to give me 28.2918, etc., is equal to 0.3989x. So I solve for x by taking this and dividing by 0.3989. And what I get there is 70.92. I want to go to 6 significant figures, so 0.9246 AMU. This is my answer. That's the mass of gallium-71. So again, if I know this is actually an equation with two unknowns, this is my second equation that I use. If I have two unknowns, I have to solve them simultaneously. One equation is going to give me something I can plug into the second equation. In this case, I just went ahead and did that math because it was very simple. But what I get is that the mass of the gallium-71 isotope is 70.9246 atomic mass units. Now, I talked a little bit about mass spectrometry, which is an instrument. The mass spectrometer is an instrument that actually can determine the masses of atoms and the percent abundance of isotopes. So this technique separates particles according to their mass. This would be a very simplistic trace. If I ran chlorine through the mass spectrometer, I have two isotopes, The most predominant isotope is chlorine 35, and it's in a ratio of about 3 to 1. If I could actually measure this and then measure this, add them together, I would take the measurement of this divided by the total, and I could get the percentage of the isotope. This is what happens. I have my sample coming in here. My heater vaporizes the sample. An electron beam is going to ionize that sample. So I get what's called a molecular ion. I have 2 electrically charged plates, which accelerates the particles. Then I go into a magnetic field, which separates the particles based on the mass to charge ratio. The lightest particles are going to come off first, and then the heavier particles, and this is my detector. Now, whatever sample is, I know it has 3 different isotopes, and I can calculate the mass of each individual isotope. In our lab, we actually do a lab. It's really unfortunate that we're not in the lab to do this, but if you had a mass spectrometer available, you could run the mass spectrometer and figure out the percent abundance and then look at the masses of the individual isotopes. It's actually pretty cool. And that is going to be the end of this part. We're going to have a 3rd lecture for this module, which just goes over the periodic table, and we're going to start that next. But right now, I'm going to stop this share and then say goodnight for right now.